All right, let's talk about the word function. It's a simple word, but it's one that bridges two completely different worlds: the abstract world of pure mathematics and the very concrete world of computer programming. We're going to dive into what a function really is and how this one word can mean two things that are surprisingly different yet deeply connected.
So, what exactly is a function? You've definitely heard the term, right? Maybe it gives you flashbacks to high school math class, or maybe you see it every single day when you're coding. But here's the big question. When a mathematician and a programmer both say function, are they even talking about the same thing? Well, the answer is kinda. It's a little more complicated than you might think.
Okay, so just take a look at these. On the left, you've got your classic math formula. Pretty standard stuff. On the right, that's what a function looks like in the Kotlin programming language. They look almost identical, don't they? Both of them seem to do the exact same job. You give it a number, it cubes it. But trust me, the story here is way more interesting than just a simple copy-paste. To really get what's going on, let's start with the common ground. What's the fundamental DNA that both of these functions share? What's the core idea that unites them? At its absolute heart, a function is just a rule, a super reliable rule. You put something in, and you are guaranteed to get one and only one specific thing out, every single time. Think of it like a coffee machine. You put in a coffee pod, that's the input, and you get a cup of coffee, the output. You're never going to get tea. That's the core promise. And in technical terms, that input is called the argument, and the output is the dependent variable because, well, it depends on what you put in. Now, in the world of pure math, this whole machine is just an idea. It's totally abstract. This formula, f of x equals x cubed, doesn't actually do anything in the physical world. It just describes a perfect, unchanging relationship between numbers. You tell it the input is 2, it tells you the output is 8. Simple, clean, and totally conceptual. And this is where that abstract idea gets its hands dirty. This piece of code isn't just a description. It's a concrete set of instructions for a computer to actually follow. It literally tells the machine, hey, take this integer, multiply it by itself 2 more times, and then hand back the result. The outcome is exactly the same. Put in 2, get out 8, but now it's a real process that's happening inside a physical machine. So you see the pattern here, right? It doesn't matter if you're in a calculus class or code editor. It's always the same powerful 3-step dance. Input, process, output. This is their shared blueprint. But, and this is a really big but, the devil is in the details. Okay, now for the really interesting part. This is where we start to see the huge gap between a perfect, clean idea and its messy, complicated, real-world application. This table really nails the core differences. On one side, you've got the mathematical function. It lives in a world of abstract perfection. Its domain, the set of numbers it can work with, is often infinite, and it's always pure, which means its one and only job is to calculate a result, period. Then you look at the programming function. It has to operate within the messy reality of a physical computer. For instance, a standard integer in a language like Kotlin is stored in a fixed amount of computer memory. That means it literally has a size limit. It can't be bigger than this number right here, a little over 2 billion. If you try to give the function a number larger than that, the program might just crash. It runs out of room. That's a hard physical limit that just doesn't exist in the beautiful, boundless world of math. And here's the other massive difference: side effects. A programming function can do more than just return a value. It can print something to your screen, save a file, or change some other variables somewhere else in the program. It's like a chef who not only cooks your meal, but also rearranges the furniture in the dining room. It's incredibly powerful for sure, but it also makes things way more complex and can be a huge source of bugs. So with all these differences, you might think the two worlds just drifted apart. But what's so fascinating is how the story comes full circle, with programmers now looking back to the pure mathematical roots of the function to build the technology of tomorrow. I mean, just look at this history. The idea of a function has been evolving in math for over 300 years. It started with Leibniz way back in the 1600s. It was refined over centuries by giants like Euler and Dirichlet, long before the first computers were ever imagined. Then, bam, the 1950s roll around and computer scientists adopt it as a core building block for writing software. So what happened next is pretty cool. After decades of dealing with the messiness of side effects and unpredictable code, programmers started getting nostalgic. They started to miss the simplicity and the total predictability of that original mathematical idea. They wanted that purity back. And this is the key concept they decided to borrow back from math. They called it a pure function. A pure function is basically a programmer's attempt to recreate a true mathematical function. For the same input, you will always get the same output. And, crucially, it has absolutely no side effects. It's a function you can completely trust to do its one job, and only its one job, perfectly, every single time. This desire for purity was so powerful that it sparked an entire style of coding called functional programming. Think of it like building with Legos, where the pieces can't be changed once they're placed. It makes the whole structure incredibly stable and predictable. This approach to writing software makes it far more reliable and way easier to test, which is a massive deal when you're building the kind of complex systems we all depend on every day. So the big takeaway here is how one simple idea, one definition, can bridge two completely different worlds and end up driving incredible innovation. We've seen the whole story arc now, haven't we? The function started out as this perfect abstract concept in mathematics. Then it was adopted by programmers, who made it more practical and powerful, but also a lot messier. And now, to build better software for the future, programmers are looking back and trying to recapture that original purity and elegance from their mathematical ancestors.
This whole journey from calculus to code leaves us with one final, pretty thought-provoking question. If a 300-year-old math concept is still revolutionizing technology today, it really makes you wonder, what's the next big idea out there? What other brilliant concept is just sitting in a dusty old math textbook waiting for someone to realize it's the key to changing the world of code all over again?